Okay, so before we go ahead and start 2.6, I got just a couple of housekeeping items very quickly, with it being Thursday and all. So tomorrow morning, that is the deadline, 8:05, if anybody's still looking to retake last week's exam. So you don't have to have any of the homework assignments completed. I would encourage you to look at them, but if you just come on in, say I want to retake the exam, you're good to go. Okay. And I also want to remind you about this coming Monday evening over at Coronado. This is going to be March 10th from 5 to 7. We've got our second AP prep session. So over the 2 hours, we're going to talk about exponentials and logs. And then the second hour is going to be my portion of the presentation, graphing trig functions. So if you're able to show up, I mean, we'd love to see you there. It's not mandatory, but if you need to show up late or you need to leave early, that is perfectly fine too. How many people think they'll be able to show up on Monday? Okay, 1, 2, so 2. Okay, I'll take it. All right. Well, let's go ahead and get started. Throughout this course, we'll have many opportunities to work with and create models based on a given data set. We've actually done that for quite a while now. 3 particularly important examples are linear, quadratic, and exponential. Because these 3 types of models occur frequently in the real world, there's a heightened focus on them in AP Pre-Cal. So now on the AP exam specifically, students will be expected to determine which model is most appropriate given a set of data. Okay, there are a few strategies and methods that we can use to determine whether a linear, quadratic, or exponential is the best one. Okay, so looking at this table below, okay, each row is going to give you a scatter plot. You have a table of data, and then it's going to show you the important features. So the first one here is linear. All right, it says use a linear model when the data reveals a relatively constant rate of change. Now, in previous lessons, when we were looking to identify whether a data set was linear, we were looking to have the exact same slope over and over again. But see, this is the issue when you start collecting data out in the real world. It's very, very rarely, if ever, going to be perfect data. So we try to model what we have the best we can. Okay, so I've already started taking a look at this. The first 2 ordered pairs, 0, 1, and 2, 2.6, you'll notice I've already found the slope. The difference of the y's over the difference of the x's, okay, so that's 0.8. Okay, so let's try the next pair of coordinates. So 2, 2.6, and 4, 5. So this would be 5 minus a 2.6 over a 4 minus 2. Okay, somebody help me out with this. Okay, what would be my slope between those 2 points? William, what do you get? 1.12? That's okay. I got something close. Okay. I got 1.2. Anybody want me to go ahead and check that in the calculator? Okay. Now, here's what I want you to do. Okay. For the next couple of pairs of coordinates, go ahead and find me those slopes as well. Between 4, 5 and 6, 6.4, and then between 6, 6.4 and 8, 8.7. Let's see what we get. Okay, give you a few seconds, and then I'll go ahead and call on some folks. Okay, Alexandra, do you have the next slope? 0.7. Okay, I got 0.7. Perfect, perfect, perfect. Okay. And Quinn, do you have that last one? 1.15. Perfect. Okay, so this is what I was referring to. We don't have the exact slope over and over again, but they're relatively close enough that we could go ahead and justify using a linear function as a model. I mean, even if you look at the scatter plot right here, those points are not exactly collinear, but they're still really, really close to that line. Okay, so that's what we're going to be looking for if we believe it's linear. Okay, let's scroll on down here. Quadratic. Use a quadratic model when the rates of change are increasing or decreasing at a relatively constant rate. Okay, so we've seen that before, okay, in previous lessons. Now, data generally follows a U-shaped pattern or upside down. Okay, so what it means is you should be able to somewhat see the symmetry of your y values in the table. So the y values will first decrease and then increase, or they could increase and then decrease. Does someone know? Hey. Let's see. There you go. Yes. Very well. Okay. So what we're talking about here is being able to see some symmetry, or at least something similar to what you would say is symmetry in the problem. So let's go ahead and take a look at this data. If I go ahead and compare the top output to the bottom output, so we have 8.8 compared to 9, I mean, those are really close to each other. If I go ahead and start to move in towards the center, well, then I've got a 3.95 compared to a 4.2. So you can see that we kind of have symmetry there. Again, it's not going to be perfect, but they're going to be pretty close to each other. Okay, or as it says here, relatively close. Is everybody okay with that? Okay. And then this is what we've been talking about a lot over the past couple of weeks, exponential. Use an exponential model when the output values are roughly proportional. Now remember, this says each successive output is approximately the result of repeated multiplication. So I should be able to take the first value, the y, multiply it by some value all the way down the line and generate that pattern. So let's see if that's what we have here. How would I get from a 0.5 to a 1? What would I have to multiply 1/2 by? Times 2. Well, let's see how close we actually get. So if I take 1/2 times 2, well, that does give me 1. Okay, 1 times 2 will give me 2. 2 times 2 will give me 4. 4 times 2 will give me 8. And if I go ahead and compare the values, again, they're pretty close to each other. Okay. Again, it's not meant to be perfect. We're just trying to find the best model for the data we have. Is everybody okay with that? Okay. Well, let's go ahead and put this into practice. Okay. Selected values from several functions are given in the tables below. Sketch the scatter plot for each, and then determine if a linear, quadratic, or exponential model is most appropriate. Okay. Well, here's the thing. We're going to go ahead and try this a little different. Instead of just going straight to the scatter plot, well, why don't we go ahead and actually look at the data? Let's make our determination, and then we'll draw the scatter plot and see if we were correct. Okay, so here's my first table where the y values are 11, 8.2, 5, 2.3, and negative 1. Okay. Is there any of the three, linear, quadratic, or exponential, that I can immediately just get rid of? I'm already thinking of one. Why quadratic? There's no symmetry. If I go ahead and start from the top and the bottom and I start comparing, like this negative 1 right here, that is nowhere near that 11. Okay, so there's no symmetry to be seen, or at least roughly symmetry, so it's not quadratic. Now, if it's linear, then we should see relatively same slopes, okay? Or if it's exponential, we should see some kind of proportional pattern. What do you folks think it is? Linear or exponential? Linear? Okay. Well, if it's linear, then let's go ahead and take a look at our slopes. Okay, so let's start this. The difference of the y's, 8.2 minus 11 over 2 minus 0. Okay, well, if I'm remembering this off the top of my head, I want to say that's a negative 1.4. Okay, let me double check that to make sure I got that correct. Okay, I did. All right. So what I want you to do is take a few seconds, just like we did on that first example on the previous page. Go ahead and find me the slope, okay, from each consecutive pair of coordinates, and let's see what we end up with. So the next one, we need to find the slope between 2, 8.2 and 4, 5. Now, all of these are going to be negative. Does anybody have the next one? Okay, it should be a negative 1.6. Perfect. Now I need 4, 5 and 6, 2.3. Okay, once again, it's a negative 1 point. Now it's 7. I'm getting something different. I got a 3, 5. Negative 1.35. Does anybody want me to actually work that out? And then what about the last one? Between 6, 2.3 and 8, negative 1. Negative 1.65. There we go. Negative 1.65. Okay, so we decided to go ahead and run with the idea that it's linear. Well, they're definitely not exact, but are they relatively close to each other? Yeah. It's not perfect, but yeah, it's almost consistent. So I'd go ahead and say, yeah, this is linear. Okay. Then with this in mind, let's go ahead and see what the scatter plot looks like. So we have 0, 11. Okay, so 2, 8.2, 4, 5. We got 6, 2.3, and we'll finish up with 8, negative 1. So that's just going to be right here off our grid. Okay, so if I were to go ahead and put a line through here, yeah, I'd say linear is going to work pretty well. Okay. Questions? Okay. All right, well, let's go ahead and do this. For B, C, and D, we're going to divide and conquer. Okay, so you two ladies right here, you're going to take care of B. Okay. You four in the middle, you're going to take care of C. And then you final three by the windows, you're going to take care of D. Okay, so focus on your one particular problem. Let me give you a minute. Go ahead and look at it if you want to go ahead and talk with those around you to help you out. But then somebody from the group is going to go ahead and tell me what they believe it is, linear, quadratic, or exponential, and why. Remember, don't look at the graph just yet. Look at what patterns you see in the table. That's what I want. Okay, so for B, ladies, what do we think? Why? Because the symmetry, okay. If we go ahead and start comparing, like 2.25, that's pretty close to 2. 5.75 is really close to 5. Yeah. So the values increase and then they decrease. Okay, so that's good. Good, good. Thank you. Go ahead and put that in the tray. So we believe this is quadratic. And let's go ahead and plot this and see how it turns out. So negative 1, 2, 1.5, 5.5. Hey, you're welcome. See you later. Okay. 4, 10.5. Okay, 6.5, 5.75. And then we have a 9, 2.25. Okay. Here we go. Okay. So I would definitely say that a quadratic is going to be better than linear or exponential. Okay. Maybe this could be something else. I don't know, maybe a flipped absolute value, but for the three, I would say quadratic is the best. Okay. Good, good, good. All right, fantastic. Okay, you folks in the middle. C. What are we thinking? Exponential, why? Okay, so what does it look like they're multiplying by? Close to -2? 1/2. There we go. Okay. So let's do a couple of these. Like if I were to multiply through by 1/2, because we're believing this is exponential. So half of 10, well, that's 5. Half of 5 is 2.5. Half of 2.5 is 1.25. And then what's half of 1.25? That's a point. Okay. So see, it's pretty close to what we got. All right. So I would say, yeah, we could roughly see that pattern of proportionality in there. So I'd agree that it's exponential. Let's plot the points. So 110, 3, 5.2, 5, 2.4, okay, 7, 1.3, and 9.7. Okay. Yeah. And I mean, it makes sense that it looks like we got a decay function because we're roughly multiplying by 1/2 each time. Okay. Good, good, good. Is everybody starting to get the idea? Anybody confused? Okay. D, last folks over here. What are we thinking? Exponential. Why? So what do you think your factor is? 1.5. There we go. And if you go ahead and do the same thing, again, it's not going to be perfect, okay? But it's going to match those up pretty well. 2 times 1.5 is 3. 3 times 1.5 is 4.5. But I believe when you get to the end, I think it's like 1.52. So it's just slightly off. Okay, good, good, good. So we're saying this is exponential, and let's see what we got here. So -2, 2. 1, 3, 4, 4.5. 7, 6.75, and 10, 10.25. So probably right about there. So there we go. All right. Okay, questions. Anybody having a hard time? Cool, 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 cool. Hey, we actually don't have a whole lot more to do. Now, you remember several lessons ago, I introduced the idea of a residual. So I want to kind of bring that back today and help you remember how to find it. Because what we're going to do tomorrow is we're going to be able to use a residual plot to help us determine if a model is appropriate for a set of data. But I'm getting a little ahead of myself. When we create a model, we can use our model to predict values for the dependent variable, the output, the y's, given an independent variable input, the x's. When using a model, it's important to remember this is only a predicted value. If we use the input value from a known data point to find a predicted output using our model, the difference between the actual and the predicted is what we call a residual. You have to subtract them, but it's super important. It's always the exact value minus the predicted. Okay. Well, with this in mind, here's our last problem. The weight of newborn babies can be modeled by a linear function for the first 4 months after birth. Selected values for the weight W of t in kilograms of a particular newborn baby are given in the table above, where t represents the number of months since birth. Use the regression capabilities on your calculator to find a linear model in slope-intercept form for the weight in kilograms of this particular baby X months after birth. Okay, well, we got to put the data in. Okay, so you folks are going to walk me through this because unfortunately I don't remember how to do it. Okay, so I'm going to go back to my calculator. Okay, so I am on my home screen. Okay, where do I go? How do I input my data? Okay, table? What do you mean? The teal thing. So down here? Okay. There we go. That'll take me right to my spreadsheet. Okay. Normally we go ahead and choose lists and spreadsheets. I like seeing the other ways to find this. Now the table has values of T for time and W for weight. I'm just going to go ahead and default back to X and Y. What do we do about this equals row though? Nothing. Leave it alone. Remember, don't ever put anything in there. Okay, so my time values are between 0 and 4 months. Okay. And then we want the weight in kilograms for each time. So 3.2, 4.2, 5.1, 5.8, and 6.4. Okay. So now I've got my data in. Okay. Ryan, where do I go from here? Go back to the menu. Okay, go back to home. Okay. There you go. Then we want data and statistics down at the bottom. Okay. Now, Ayla, how do I organize the information? Not menu. Tab. Now you can also use the touchpad on your calculator and use your mouse to go ahead and click where it says, add variable. You can do it that way. I've always done it with tab. There are my two headings. Okay. Click tab again. Now we'll do the vertical. So there we go. There's my scatter plot. Now I wanted to go ahead and draw that trend line, the best fit line, and give me the equation. Okay. Audrey, do you remember how to do that? Menu. We're going to analyze, regression, and then I would choose what kind of model I believe it is. Now, let me ask you a question here. There's two linear functions. Does it really matter which one I use? No, it's just basically how you want it written. Do you want your equation to start with the slope or the y-intercept? Now, I'll just keep it consistent because it says a plus bx on our paper, but it does not matter. So here's my line. And there's my model, 3.34 plus 0.8x. Okay, perfect. So I come on back over here. Okay. That is what we got. Now, of course, I went ahead and wrote it on my paper using the W and T, but if you just said y equals with x, you're fine. That's not going to change anything. Okay. Now, part B, use this model to predict the weight in kilograms of a baby that's 2.5 months old. Okay, so we're going to go ahead and take this function. Okay, so if I could write, so W of 2.5 equals the 3.34 plus 0.8 times the 2.5. So somebody help me out here. What am I going to get? .34 kilograms. 5.34 kilograms. Okay, now that's our predicted weight based on our model. Now in part C, the actual weight of a 2.5-month-old baby is 5.5 kilograms. What's the residual for this weight? Okay, now I remember for the residual, we got to subtract them, but is it actual minus predicted or predicted minus actual? Okay, Bailing, which one was it? Actual minus the predicted. Okay. So the actual is 5.5. We found our predicted to be 5.34. Okay. And Matthew, what is that difference there? What's a 5.5 minus 5.34? Okay, so 0.16. That's my residual. That's all a residual is. It's the difference between the exact value and your predicted value. Now it says, did our model under or overestimate the weight of this baby? It underestimated, yeah. Okay, we got a predicted value that was smaller than the exact. In fact, this is how you want to think about it. If your residual is positive, then that means it's an underestimation. If your residual is negative, then that means it's an overestimation. It's always actual minus predicted. Okay. All right. And that's where all the other classes got. We're not going to go ahead and use a residual plot until tomorrow to show us if a model is appropriate, but are there any questions? Anybody having a hard time with anything? All right, then we are done.